So let's add a little bit more about ocean processes, but mostly air-sea interactions. The main problem, as I see it, with doing air-sea interactions, and typically that means mixed layer heat budgets, sea surface temperatures, how they are determined at the interseasonal timescale. And the problem with this, well, at least the challenges are that the data is never good enough to actually resolve these purely from data in terms of the spatial and timescale resolutions. These are moving features with certain spatial scales, and sea surface temperature scales are a couple of orders magnitude smaller than the atmospheric scales, let's say in the case of MJOs, and the heat flux measurements are always problematic, and you need the mixed layer depths, vertical temperature gradients, this, that, the barrier layer, and so on and so forth. So either we use what are called reanalysis, where the models and data are blended together, but those don't always conserve mass, heat, and so on, or there are problems with the way they do mixing and so on and so forth. And or you use models, and the problem with models is different models may produce slightly different heat budgets and so on. So I'm going to finally succumb to the pressure and try to use a laser pointer here. So maybe this works better. Okay, sorry. All along I could have probably done it, but I haven't done it nonetheless. This is from Harry Hendon's chapter in the Lau and Walliser book. Is showing a schematic diagram of the magnitude and phase relationship relative to the convective anomaly of surface fluxes and SST variations produced by the canonical MJO. Hundreds of papers have been done on heat budgets, air-sea interactions for the MJO. Very few exist for the mesos, so we will use MJOs again to try to understand some of the challenges and the relative phasing and so on. So the asymmetric zonal scale of the cloudy windy phase and the suppressed calm phase, as well as the eastward phase speed of around 4 meters per second of the joint atmosphere ocean disturbance across the wormhole are indicated. Typical extrema of surface fluxes and SST over the life cycle of the MJOs are shown for the Western Pacific. So when we talk about the ocean atmosphere disturbance, the scale is one thing, but you also have to look at the numbers. So we are looking for the scale here of 8,000 kilometers in the cloudy phase and the convective phase, and 10,000 kilometers in the dry phase. Remember, they are propagating eastward from the Western Indian Ocean. So you have coldest SSTs of 29.2 degrees here in the convective phase, and the warmest SSTs here are 29.7 degrees centigrade. So the first problem to think about is there is this 0.5 degrees centigrade difference, and when you look at observations of sea surface temperatures, either from in situ moorings or satellite data and so on, the resolved signal itself tends to be often this small or even larger. So you half a degree may not even be completely resolved by the sea surface temperature products, and the warm temperatures mean that even a small difference of half a degree can make a big difference in terms of atmospheric response, because you are at or above the convective threshold, where when sea surface temperatures are above this convective threshold, you're going to get a strong atmospheric response. So in the convective phase, you have wind stress here that is strong, associated with the convection compared to the clear phase where the wind stresses are much weaker typically, and this is moving at 4 meter per second, and this is even though we mentioned Kelvin waves and Rossby waves, the eastward propagation of the MJOs is not as fast as the MJOs, and the typical explanation given is that the propagation speed is slower because this is a coupled, convectively coupled Kelvin wave and not a free Kelvin wave. Free Kelvin wave would move much faster. So associated with that, you have a latent heat loss from the ocean feeding the convection of 170 watts per meter squared. Take these numbers with a pinch of salt. And there is a net loss from the ocean of 80 watts per meter squared compared to the short wave that's coming in at 160 watts per meter squared, because that is inhibited by the clouds as well. And there are various theories that explain why this moves eastward, which we will come to when we do Bin Wang's chapter from this book. But ahead of, so there is cyclonic circulation, convergence, and vertical motions in the convective phase, and they hit the tropopause ceiling, and then there are divergence at the top. So there is subsidence ahead, which has a clear sky. So radiative forcing is 220 watts per meter squared here compared to 160 watts per meter squared. That's a difference of 80 watts per meter squared. That's a pretty massive difference. And the latent heat loss is reduced basically because the wind stress is reduced greatly, and of course the dependence of latent heat flux is very non-linear on temperature. It's a function of linear function of wind speed, but it depends on the difference of saturation humidity at SST and the specific humidity of the atmosphere. So that's reduced from 170 watts per meter squared to 90 watts per meter squared, because in the Western Pacific there is a loss of latent heat flux from the ocean even in the dry phase. So there is a net downward flux of 60 watts per meter squared. Okay, as I said, this is doable in a place where maybe the heat balance is mostly one-dimensional. So the quadrature relation between sea surface temperatures and net heat fluxes at intraseasonal timescales explain the major control by the atmospheric fluxes on sea surface temperature. But of course there is advection involved, dynamics involved. So depending on where you are, vertical entrainment and other terms could be important, and unfortunately the models may differ on the specific details like that in terms of the dominance of one process or the other, and these are written a lot about as well. So you should remember that. Nonetheless, air-sea interactions are critical. I should also mention that once the convective phase is done, sea surface temperature that is cooled by half a degree here has to get reorganized for the next convective phase, and the processes involved in the reorganization are somewhat similar. Weaker wind speeds, increased downward shortwave radiation, and warming of the SST, but it depends on other details of ocean circulation as well. Similarly for the northward propagation, so this is a schematic of air-sea interaction in the northward propagation of convective anomalies associated with the ISO during boreal summer in the Indian and Western Pacific Oceans. Remember, there is East Asian monsoon and Indian monsoon, and there is a 30 to 60 day time scale in both places in the Indian and Western Pacific Oceans. Dark vertical lines indicate mid-tropospheric vertical velocity anomalies. So you have vertical motion upward in the convective phase, and you have subsidence on either side with the winds going into the screen here. So we are looking at the meridional section from south to north because we are looking at northward propagation. So you have winds coming towards you and winds going away from you. So that's the tail of the arrow and head of the arrow here. And this is the vertical scale in pressure coordinate. So again, in the clear phase there is downward shortwave radiation, and the phasing here is such that the latent heat flux and humidity and moist static energy are positive in the convective phase, where the ocean is supplying the heat, and ahead of it there is reduced latent heat flux, there is increased latent heat flux here, so ocean is losing and pumping it into the atmosphere. There is low level convergence here and divergence behind it. Skin temperature is warmer here and colder over here, and this is the downward shortwave radiative flux, and LQ is the latent heat flux multiplied by specific humidity. So this is positive here and negative here. So the stronger winds and cyclonic circulation increase latent heat flux, the cloudiness reduces the downward shortwave radiation flux here, whereas it's positive on the other side. So again, now you see that there are not even numbers put on here. So this is how air-sea interactions are typically evaluated. It's always a challenge, but the main thing you're often trying to do is to see if ocean dynamics have a role to play, or if the heat budget is mostly closed by net heat flux, explaining the SST variations. Nonetheless, looking at the ratio in terms of percentage of intra-seasonal, so 30 to 90 day period SST variance to total subseasonal, which is defined here as 10 to 200 day period SST variance for this period of July 1, 1986 to June 30, 1993. So the shading levels here begin at 45% and scale up to 50% and 60%. So you can see that there is a strong 60% or more of the 30 to 90 day variance here, where the MJOs come along and then they have to either cross the maritime continents here. Many of them are detoured southward. There are studies explaining why that happens, whether it's because of atmospheric processes or ocean processes. There seems to be strong air-sea interactions involved in the detouring as well. That detouring comes in here between Indonesia, New Guinea and Australia, and affects the South Pacific convergence zone, so you get the 30 to 90 day variance here as well. And of course there are many MJOs that cross over and produce 30 to 90 day variance, but there are also internal variabilities here that we will see later on, that are the so-called tropical instability waves, which are related to the barotropic instability in the ocean. So they are intrinsically generated. They also project onto this intraseasonal time scale. Okay. There are lots of moored arrays in this area which have been analyzed quite a lot to understand the processes. To look at the heat budgets of the SST variability, so we are looking here at observed sea surface temperatures and temperature at 9 meters. So you can see that sea surface temperatures and 9 meter temperatures are very different, so that by the time you get a few meters below the surface this very fast diurnal time scale variability disappears. So this is showing time series of air-sea fluxes and SST from Hui IMET mooring located in the intensive flux array during the Toga core, which was conducted during October 25, 1992 to March 1st, 1993. Net heat flux and rainfall were averaged over 24 hours. So here is the net heat flux. Daily means are shown in watts per meter squared. Rainfall in millimeters per hour, but as daily rates. Wind stress here, zonal wind stress, and observed SST smoothed every 2 hours. And there is a one-dimensional model that is run to forced with these observed fluxes to understand whether the model can reproduce the observed variability. And you can see the differences here. This peak is quite high. The model doesn't quite capture it, but here the model is overdoing compared to observations. But there are also other issues. For example, if you forced the ocean with observed surface fluxes, you're essentially assuming that the atmosphere has infinite heat capacity and the fluxes are forcing the ocean, whereas it's the ocean that has high heat capacity and the atmosphere responds rapidly to sea surface temperature changes because of its low heat content, low density, and so on. So one has to be careful in doing this, but nonetheless these are done to see if one-dimensional balance can explain the observed sea surface temperature variabilities. Again, these are great challenges, but nonetheless these exercises are very important to try to understand the processes and advance the prediction efforts of MJOs and so on. So here, predicted SSTs at the IMET site for October 22, 1992 to March 1993 using hourly surface fluxes from IMET mooring data in the thick curve here. So and daily mean fluxes dashed curve and SST differences between the two experiments is shown in A, and this is from a modeling experiment of Shinoda and Hendon. So the point is that if you look at the hourly forcing and daily mean forcing sea surface temperatures, hourly forcings capture the variations better. These are in days, and the smoothing of the fluxes obviously smooths out the sea surface temperature variance and variability, and the differences are not small. They are of the order of the sea surface temperatures associated with the difference between the clear phase and the convective phase of the MJOs. Okay, but the spatial scale of the SSTs also matters because convection tends to be organized at the sharpest gradient and not at the maximum sea surface temperatures. I'm just saying that. If you don't understand what it means, don't worry, but if you do want to understand more, there are very nice papers by Mitch Moncrief and others that explain this kind of relation. Okay, so what is it that you want to conclude? Basically, air-sea interactions are very important at interseasonal timescales, both for MJOs and mesos. And as we saw before, the Bay of Bengal has almost a one-dimensional balance. Western Pacific has almost a one-dimensional balance. So the net heat fluxes can explain large part of the SST variability. But if you go to the Eastern Equatorial Indian Ocean, ocean dynamics play a role. If you go to the Eastern Pacific Ocean, ocean dynamics play a big role, and so on. So we have to be keenly aware of these sorts of issues. And then there are lots of issues about models, whether they can capture the vertical processes because their vertical resolution is not high enough to capture the mixing and entrainment processes, and so on and so forth. And when you are looking at temperature differences of half a degree and fluxes are coming from observations, oftentimes it's hard to blame the models because the flux errors could be order 10 watts per meter squared, which could explain the model errors. So you don't know whether the difference between observed SST and model SST came from errors in the fluxes or errors in the model. These kind of issues remain. So if you don't know what I mean, don't worry about it at this stage, but you can read some good papers on those type of topics as well.